Okay, welcome back to the second part of Lecture 28. We're now going to take a look at how we can manipulate the time-ordered product in such a way that we can calculate it exactly. It turns out that the strategy we're going to be using is a factorization of the time-ordered product that we're going to factorize in a couple of different stages in order to ultimately get the final time-ordered product. So the starting place is to begin with the interaction representation, and as you recall, the interaction representation writes the Schrodinger wave function as e to the minus I over h bar h0 t time-ordered product of the exponential of the integral of the interaction representation potential, where the interaction representation potential vi of t is given by e to the I over h bar h0 times t, v of t e to the minus I over h bar h0 t. And all of that will be acting on the Schrodinger wave function at the initial time. Now in our case, we have an explicit v of t, so we can explicitly calculate vi of t. The h0 that we use is the time-independent simple harmonic oscillator Hamiltonian. The term that has the 1/2 in it is just a number, and because I have Hermitian conjugates on both sides of the similarity transformation, those constant terms will just cancel, so I don't even write them down in the next expression. What we get for vi of t is e to the I over h bar omega a dagger a times the time t. Notice that the 1 over h bar and the h bar will cancel, so it ends up being e to the I omega a dagger a times t. That's going to act on the two variables f, which is just a number, it's a function of time, times a dagger plus f star times a, and then I have a e to the minus I omega a dagger a times t as the right-hand side of the sandwich. Now, we're going to show you how to work out e to the I lambda a dagger a dagger e to the minus I lambda a dagger a. If you think in terms of Hadamard, this is a relatively simple operation to go through, but we're going to actually use this other trick where we're going to think of this as a function of lambda. We're going to take the time derivative with respect to lambda, and then from that time derivative, we're going to go ahead and find an equation of motion for this similarity transformation of the a dagger operator. So when we look at the first time derivative, we're going to pull down a commutator with an a dagger a overall factor of I that we can pull out to the left. So I e to the I lambda a dagger a, commutator of a dagger a with a dagger, e to the minus I lambda a dagger a. We'll call that the time derivative of g of lambda with respect to lambda. The commutator is easy to work out. It simply gives a dagger. And so what we find on the left-hand side is it's just equal to I g of lambda. So I find dg of lambda d lambda is ig of lambda. Well, that's simply an exponential function. So we get g of lambda is equal to g of 0 e to the I lambda. When we plug that in, and we're going to have to take the Hermitian conjugate of that expression to get what the time dependence of the a operator is, we simply get the interaction representation for the potential is equal to f of t e to the I omega t a dagger plus f star of t e to the minus I omega t times a. Now, one of the things that we need to note is that this interaction representation operator, if I look at its commutator at two different times, we can easily work that out. The only terms that contribute are the commutator of a dagger with a and the commutator of a with a dagger. Each one of those commutators will give us a separate contribution. So when we work out the full expression, we'll get an f of t times an f star of t prime, e to the I omega t e to the minus I omega t prime, commutator of a dagger with a. And then the second term will be plus f star of t, f of t prime, e to the minus I omega t, e to the I omega t prime, times the commutator of a with a dagger. We drop the terms that involve the commutator of a dagger with a dagger and with a with a. Please be sure that it's clear to you exactly how to do this calculation. It's important that you're able to do these kinds of manipulations. Using the fact that the commutator of a dagger with a is equal to -1, the commutator of a with a dagger is equal to +1, we see that this is the difference of two Hermitian conjugates. So it's minus 2I times the imaginary part of f of t times f star of t prime e to the I omega t minus t prime. The important thing to note is not necessarily the exact value of this expression, although we might need that in the future as we're continuing with the calculation. What's important to note is that that is a number, not an operator. The conclusion we reach from this is that the commutator of vi of t with vi of t prime is an object that commutes with all operators because it's a number, not an operator. That is a huge simplification. In most time-dependent problems, we will not find that vi of t prime commutes with all other operators. But it does in this case, and it does because the commutator of a dagger with a is a number, not an operator. In order to proceed further, we're going to want to actually be explicit about the function that we're using, and we're going to pick the function f of t to be c e to the I big omega t, where c is a real number. Looking at the expression for vi of t at the top of the page, we can easily substitute in what f of t is, and what we find is this expression at the bottom that I'm going to now move up to the top. We get that vi of t is equal to that real constant c times e to the I little omega plus big omega times t, a dagger plus e to the minus I little omega plus big omega times t times a. Okay, if we now put this back into the general expression that we got for vi of t commutator with vi of t prime, we find we get minus 2ic squared, the imaginary part of e to the I big omega t minus t prime e to the I little omega t minus t prime. That's actually quite easy to find the imaginary part of it, so we find that the expression is equal to minus 2ic squared sine of little omega plus big omega times t minus t prime. Okay, good. We have our concrete expression for the commutator of vi of t with vi of t prime. Gottfried now says, let's consider the following object. It is by no means obvious that this is a good thing to try, but perhaps if you're thinking about what you would do, it's kind of a natural expression to think about because it is something that would arise or could arise as we're evaluating a time-ordered product. We're going to call this operator w hat of t, and it's the integral from 0 to t of v interaction of t prime dt prime. Now, because we have an explicit form for v interaction of t, we can just go ahead and evaluate this integral because the functional dependence in vi of t is just exponentials. And when I take an integral of an exponential from 0 to t, I get 1 over the coefficient in the exponent multiplied by e to the I, whatever the coefficient is, multiplied by t, minus 1, because the exponential of anything times 0 is just equal to 1. And in this particular case, what we'll get is c over I omega plus big omega multiplied by e to the I little omega plus big omega times t minus 1 multiplied by a dagger. And then when we look at the expression for that is the coefficient of the a term, it is the complex conjugate of that. So it's going to be minus c over I little omega plus big omega times e to the minus I little omega plus big omega t minus 1. Okay, armed with this, now that we have an explicit expression for w of t, we can calculate the commutator of wt with v interaction of t. Note that I'm doing this commutator at the same time. This is not a commutator between two different times t and t prime. It's a commutator between two objects at exactly the same time. Again, the only terms that are going to contribute are the a dagger and a commutators, or the a dagger commutator. The a dagger with a dagger and the a with a terms, those commutators are both equal to 0. So you can pretty much read off exactly what it's going to be. We have vi of t at the top of the page. We have w of t in the upper part of the page, just above the halfway point. So when we collect those terms, the term that is multiplying the commutator of a dagger with a is c squared over I little omega plus big omega, 1 minus e to the minus I little omega plus big omega times t, multiplied by minus 1 because the commutator of a dagger with a is minus 1. And then the second term that we're going to have is a minus c squared over I little omega plus big omega multiplied by 1 minus e to the I little omega plus big omega times t. Okay, we can add those two terms together, and just looking at the relationship between exponentials and sines and cosines, we can get the final number, which is going to be minus 2c squared over I little omega plus big omega multiplied by 1 minus the cosine of little omega plus big omega times t. And again, that is just a number. Okay, you can see because of the minus 1 in the first term, the constant terms add together and the exponentials add together, but they each have a minus sign. That's why we get 1 minus the cosine. And again, the big point is that that's a number. So w of t commuted with vi of t is an object that will commute with every operator. All right, we're now going to make a unitary transformation. We're going to take our initial time-dependent wave function in the interaction representation. We're going to rewrite it as e to the minus I over h bar w of t times what we're going to call psi 2 of t. And what that essentially means is psi 2 of t is equal to psi interaction of t multiplied by e to the plus I over h bar w of t. It's a simple transformation we're making on the wave function, and we're going to now look at what is the equation of motion for psi 2 of t. Before we do that, I have to remind you what the equation of motion was, or if you like, what the time-dependent Schrodinger equation was in the interaction representation. If you recall, what happened there was we lost the h0 from the Hamiltonian. So what we find is I h bar d by dt minus vi of t acting on psi I of t is equal to 0. And that's the time-dependent Schrodinger equation in the interaction representation for the interaction representation wave function. All right, it's just a little bit of algebra now to calculate the expression for the equation of motion for psi 2 of t. What we're going to do is we're going to take that old equation of motion. Let me bring that back up on the screen. We're going to take that old equation of motion. We're going to multiply it on the left by e to the I over h bar w of t. I'm going to introduce the factor of 1, e to the minus I over h bar w of t, e to the plus I over h bar w of t, in between the square brackets and the wave function in the interaction representation. Now if I group e to the plus I over h bar w of t and psi I of t, that's the object psi 2 of t. And now you see what we have is the similarity transformation of this differential operator. I would like to spend a moment talking about this. The first thing you might think is, well, look, the derivative of w of t with respect to t is just vi of t. Let's go back and take a look at the definition of w of t. You can see because it's defined as an integral of vi of t prime dt prime, if I take the time derivative of w of t with respect to t, I do indeed get vi of t. So you might think when we look at this expression, the derivative is going to act on that exponential term and it's going to act on the wave function. When it acts on the exponential term, I'm going to get the derivative of w of t. That's going to give me a vi of t. It's going to cancel with the vi of t that's there, and I will simply get the time derivative of psi 2 of t is equal to 0. Of course, that's not correct. And it's rather subtle why it's not correct. And if you don't see immediately why it's not correct, don't feel bad, because this is the kind of a thing that takes a little bit of experience in working with time-ordered objects to recognize that. Remember, w of t does not commute with vi of t. And so I cannot immediately evaluate the derivative by simply taking the derivative of that exponential. The only exponentials that depend on operators that I can take a derivative of are ones that are time-ordered. If I take the derivative of a time-ordered product, the object that appears in the exponential, the derivative of that exponential, gets pulled out into the front. But this exponential is not a time-ordered product. We didn't explicitly calculate the commutator of w of t with w of t prime, but it doesn't take very much for you to see that that commutator is not 0. And so we have no idea what the time derivative of that exponential factor is. Indeed, that's really what we need to try to work out in order to figure out how to get this expression into something that we can actually work with. Okay, so the main point is that because w of t does not commute with vi of t, we cannot easily evaluate the derivative term. So instead what we're going to do is we're going to evaluate a power series expansion for the two exponential terms. Okay, so the first term is simply the exponential e to the plus I over h bar w of t. So that has a power series 1 plus I w plus 1 over 2 factorial I over h bar squared w squared plus 1 over 3 factorial I over h bar cubed w cubed, and so on. We know exactly what that power series is. We then have the differential operator in the square bracket, and then we have the exponential of e to the minus I over h bar w, so that's 1 minus I over h bar w, plus 1 over 2 factorial minus I over h bar squared w squared, plus 1 over 3 factorial minus I over h bar cubed w cubed, plus and so on. Okay, so the first thing we're going to do is we're going to act that derivative and the minus vi operator on the exponential factor on the right. So the first term is going to be an I h bar d by dt. That's the term that corresponds to I h bar d by dt acting on the 1 operator. Then we're going to have a minus vi when that acts on the 1. And then I'm going to have an I minus I over h bar multiplied by I h bar w dot plus w I h bar d by dt. That derivative term is moved to the right because the derivative acts on everything to the right. And then I have minus the vi times the w. And now when I work on the second order term, I have the coefficient 1 over 2 factorial minus I over h bar squared. When the derivative acts on the w squared, I have to take the derivative on each of the terms in succession. So I'll get an I h bar w dot times w plus an I h bar w w dot. Because w dot is equal to vi and because vi and w do not commute, I cannot change the order of those terms. I have to keep the ordering correct. And then I have plus the w squared I h bar d by dt, and then of course minus the vi times the w squared. And then similarly for the third order term, when we calculate the derivative, we'll get 3 terms, I h bar w dot w squared, I h bar w w dot w, plus I h bar w squared w dot, and of course we get the term w cubed I h bar d by dt, and the minus vi times the w cubed. Okay, and of course this expression continues out to infinity, and you can easily work out what any term is if you would like to. Okay, so now we're going to multiply by the exponential term from the left. So the 1 is going to give me I h bar d by dt. The 1 times the minus vi gives me minus vi, and those are all of the terms that are independent of w. Now we're going to collect all the terms that are linear in w. I'm going to have an I h bar w that multiplies I h bar d by dt minus vi. Those are the 2 terms that are on the right-hand side of the front line. I'm going to have the 1 term multiplying the first order terms on the right-hand side, and that's what gives us the w dot plus w d by dt plus I over h bar vi times a w. Okay, so those are all of the terms that are first order in w. We now work on all of the terms that are second order in w. The first terms involve the 1 multiplying the square terms. So those are going to be a minus 1/2 I over h bar w dot w plus w w dot plus w squared d by dt minus I over h bar vi w squared. We're now going to have the terms that involve the w on the left-hand side times the linear order terms on the right-hand side. And that's going to give me plus I h bar w w dot plus w squared d by dt plus I over h bar w vi w. And then we're going to get the terms that involve the w squared times the terms that are of order 0 in the w on the right-hand side. And that's going to be, again, minus 1/2 I over h bar w squared d by dt plus 1/2 1 over h bar squared w squared times vi. All right, now the next collection will be the cubic terms, and I'm not going to read them out explicitly for you, but again, what we do is we multiply the 1 times the cubic terms, we multiply the w times the squared terms, we multiply the w squareds times the linear terms in w, and we multiply the w cubed times the derivative and the vi term. And I don't even think I wrote all of the w cubed terms down there. And the rest end up being higher order. Now, the one thing that we have to recall, as I had mentioned before, is that w dot is the time derivative of w, and because w is written as an integral of the v interaction, that just is given by v interaction of t. All right, so we need to substitute in for the w dot. So looking at the first line, I get I h bar d by dt minus vi. The w dot is equal to vi, so that's a plus vi. And you can see that linear term in the vi cancels. The next term that I'm going to get looking at the operators, not at the derivatives, is going to be a term that is I over h bar viw. And there's a minus I over h bar w vi. So that's a minus I over h bar commutator of w with vi. When we look at the terms that involve the w times a derivative, you can see those two terms cancel. So I don't have to keep track of that term. And now we're ready for the quadratic terms. So I replace the w dot with a vi. So I get a viw plus a wvi. I get minus 2w times vi. That's coming from the next term in the first line. I will get a minus 1 over 2 h bar squared viw squared. That's coming from the last term in the first parenthesis on the second line. Let's take a look at the derivative terms. Just like before, the derivative terms, there are three of them. They cancel. So the w squared d by dt terms, they all cancel. We also have a term that is minus 1 over h bar w viw. And we have a term that is plus 1/2 w squared times vi. Okay, I haven't yet gotten to the third order terms. The third order terms are written down for you here. 1 over 6 h bar squared viw squared plus w viw plus w squared vi plus 1 over 2 h bar squared w viw plus w squared vi minus 1 over 2 h bar squared w squared vi. The derivative terms will also cancel in this case, and the rest are all higher order terms. Now what we want to do is we want to group these terms together. So as I had mentioned before, the minus vi and the plus vi, they cancel. I have an I h bar d by dt. I have a minus I over 2 h bar commutator of w with vi. That's because on the first line we have another term that involves a plus I over 2 h bar commutator of w with vi. And then we have the quadratic terms. We're going to get 1 over 3 h bar squared minus w commutator with vi multiplied by w plus w times the commutator of w with vi. You have to very carefully look at those terms to see that you can get them into that expression. You also see that that's actually a nested triple commutator. And we find that the final expression after all the dust settles is I h bar d by dt minus I over 2 h bar w commutator vi plus 1 over 3 h bar squared commutator of w with the commutator of w with vi plus higher order terms. And the key, which I haven't explicitly given to you here, is that all higher order terms are multiple commutators. But recall the commutator of w with vi was a number, so it commutes with everything. And that means I can truncate this expansion at the second term. The third term is actually 0, and so are all higher order terms. And this is what allows us to actually simplify the expression. So we can substitute in what the commutator of w with vi is, and we get I h bar d by dt plus c squared over h bar little w plus big W multiplied by 1 minus cosine little omega plus big omega times t. All right, we plug this into the equation of motion for the psi2 wave function. We get I h bar d by dt plus c squared over h bar omega plus little omega plus big omega multiplied by 1 minus cosine little omega plus big omega times t, all multiplied by psi2 of t. That whole thing is equal to 0. That can easily be integrated. We get psi2 of t is e to the I over h bar integral from 0 to t c squared over h bar little omega plus big omega 1 minus cosine little omega plus big omega t prime dt prime multiplied by psi2 of 0. And we can easily do that integral. It's just the integral of a constant and of a cosine. And our final expression is e to the I c squared over h bar squared little omega plus big omega t minus sine little omega plus big omega t over little omega plus big omega, whole thing multiplying psi2 of 0. Now, going back to our relationship between psi 1 of t and psi 2 of t, we see psi 1 of t is e to the minus I over h bar w of t psi 2 of t. We plug in what w of t is, and we get this operator expression, e to the minus c over h bar little omega plus big omega, e to the I little omega plus big omega t minus 1 multiplied by a dagger plus c over h bar little omega plus big omega, e to the minus I omega little omega plus big omega t minus 1 multiplied by a, and then we have to multiply it by this function, so it's multiplied by I c squared over h bar squared little omega plus big omega t minus sine little omega plus big omega t over little omega plus big omega multiplied by psi 2 of 0. Now, using the fact that psi 2 of 0 is equal to psi 1 of 0 is equal to psi Schrodinger of t will allow us to re-express that in terms of psi Schrodinger of t. And then finally, we get the full psi Schrodinger of t by using the expression psi Schrodinger of t is equal to e to the minus I omega t a dagger a plus a half multiplied by psi interaction picture of t. Okay. Now to check, we could compute the overlaps with states bra m and verify the differential equation for Cm of t holds that we derived in the early part of the lecture. I'm not going to do that. It's a little bit messy to try to work that out. But the summary is that when the commutator of vi of t with vi of t prime is a number and not an operator, then the time-ordered product simplifies. And in particular, what we find is the time-ordered exponential of minus I over h bar integral from 0 to t vi of t prime dt prime is equal to the time-ordered exponential of minus I over h bar c integral from 0 to t e to the I omega plus big omega times t prime a dagger plus e to the minus I little omega plus big omega t prime times a times dt prime. That's the definition of the interaction picture time evolution operator. And then we have this explicit expression that is given below, e to the minus c over h bar little omega plus big omega multiplied by e to the I little omega plus big omega t minus 1, whole thing multiplied by a dagger plus c over h bar little omega plus big omega multiplied by e to the minus I little omega plus big omega t minus 1 multiplied by a, and then multiplied by this function exponential IC squared over h bar squared little omega plus big omega squared little omega plus big omega times t minus sine little omega plus big omega times t. And that's the explicit expression. That's an exact operator expression for the interaction representation time-ordered product. We multiply it by e to the minus I omega t a dagger a plus a half on the left, and we get the full time-ordered product for this time evolution operator of this complicated time-dependent Hamiltonian. And you can see what we've done is we've actually factorized it. The first term is this exponential with an h0. The second term is another operator expression, and then we have another expression which involves a function. Okay, that's all that we have for this lecture. I hope you enjoyed seeing the details of exactly how you can develop this exact time-ordered product. It is a complicated thing. I first worked this out for this class many years ago, probably on the order of 15, maybe even 20 years ago. And at that time, I just thought of it as an academic exercise. I've actually found that I've used this in my research many, many times. It's an incredibly important expression and an incredibly important result. And I do hope that you will remember that such time-ordered products can be evaluated exactly when they satisfy this condition that v interaction of t commutator with v interaction of t prime is equal to a number, not an operator. All right, that's all that we have for this lecture. We'll see you in Lecture 29.